we are going to start with um, this problem. You remember I told you last time that we are gonna start solving problems now with magnetostatics. So here is one problem. In this is an example problem. So I give you two loops, okay? And this is now you need to get a sense of what kind of problems I'm giving. I will not ask you to derive something from scratch. That is not gonna happen. What I will ask you is to use formulas that we have derived here and in the book. I'm not gonna give you anything from the book that I have not covered. That's why I said, look at my notes. If you see something in the book which I have not covered, obviously I'm not going to ask for it, but it's always good, if you want to solve something more, do it, obviously. What I'm asking you is the minimum. It's not going to be the minimum, it's going to be adequate. Now, if you do all of this and you have time to do more, obviously. So this is an example of a problem where I give you two loops, considering that we have already solved both here and in the book. The single loop has been solved. All right, it is in the book in the solution. Okay, so I'm giving you now two loops, and I say these two loops carry two currents. They are moving along the same direction. And I'm asking you to find the field at point A, which is like halfway between O1 and O2, which are the centers of the two loops. And I just want you to find the magnetic field there. So what do I do? In cases like that, when you synthesize, that's called a synthesis problem, all right? You try to take pieces of things that we have done, and then you put them together. So here, what is that you have to use? The information about the single loop. Because we said when it comes to magnetic fields, we can superimpose. Remember I said that? Superposition is extremely important when we come to electric and magnetic fields. You can do it. You cannot superimpose power or energy, but you can superimpose fields. Okay, so here what I will do is to consider each loop separately, get the solution which we found is available, and then use this solution to find the total field. Obviously, when you go from a single solution, from one solution, to use the outcome of that solution for something else, pay attention to the variables, pay attention to orientation, all right? Just don't plug one formula, you plug it in. Pay attention to what magnetic field do I have for a given direction of the current, all right? So in this particular case, because the current moves along my thumb, then the magnetic field around that current loop is going to come up, down, up. All right, if you look at the purple loop, the magnetic field will go like this. And that's the first question in this solution. Find the directions of the magnetic field. You cannot solve a problem in electrostatics or magnetostatics without knowing how the field looks like. That's why it is important. Sometimes people say, well, we spend too much time in the fundamentals. Yeah, because if you don't know the fundamentals, you will understand the solution. I'm putting it together for you. But if you try to solve the same thing without looking at what I've done, you may find it difficult. All right, that's why fundamentals are important. What does this show here? It shows that when the current flows on the loop like this, the field lines come from underneath the loop, you see the purple ones, up, and then they will go and close somewhere far away. They will close somewhere, all right? They are not open lines, they are closed paths. But they are gonna all come, and then what is also interesting, on the surface of the loop, the purple ones, have the same direction. They all come perpendicular. If you put, say, yourself, if you were an observer and then you look just exactly what happens on the surface of the loop, you are going to see that all of these lines crossing the surface of the loop perpendicularly. Important observation. You never forget that. And then they go out of the loop and then they will close somewhere. Okay, so that is the purple. Now I'm going down to the green one, which is the second. What I also see is the same kind of thing because the currents have the same direction. All right, so they will come, the green lines, they will come underneath their own loop. They will cross the loop, the surface of the loop perpendicularly, and they will come up and so forth. And depends on how close or how far away the two loops are, some of the magnetic lines of the upper loop will cross through the lower loop. All right? That's nothing to worry about because superposition applies, which means if I were to solve only the purple loop, and then like I take away the other one, and I find the lines and the magnetic field, and then I take the lower loop and I do the same, then I can just put one on top of the other and then just sum up. Now, I have not done this here because I wanted to show you, it's more visual to see at what point there is a strong interaction. What is it now of interest here? Along this axis, where I have identified my point A, the direction of the two fields is identical. You cannot make that argument about rather any other point, but that axis. Is that clear? Because at any other point, you will have the purple lines coming with one direction, the green lines coming with a different direction. So the directions are not identical. But if you go on the axis of the two loops, the directions of the two fields are identical, which means then going back to this problem. And in fact, I have here from the book at what exercise on the book this is solved. We did it last time. The magnetic field from the upper loop, I call it H1, at point A, is going to have this form. Knowing that the direction also, you always keep in mind that the direction is positive. And then I take the field from the second loop that has the same kind of thing, and because the distance of A from the two loops is identical, that means that when I superimpose here, all right, I find the same thing. When I superimpose, is like twice as much. So at that point, at that particular point, the two loops will have together a magnetic field, which is like twice the value of the single loop. Yes. We used, well, we did not use Ampere's law for this question, all right, because it's more complex. When you use Ampere's law, no, excuse me, we use, I apologize. How did I think about Gauss's law? We use Ampere's law, absolutely, and practically in the Biot-Savart form, though. Not like the curl of H equals J. And the reason we did not use in that curl form is because then you would have to go and integrate over a surface, okay, to make it a line integral. And then because the current is here, it's not a straight line, it's not a simple. You do that in cases where your current has a very simple format, like a single line, all right? If the current is a loop, is a terminated line, it has anything else, usually you start with a Biot-Savart form, which is like which is a byproduct of the Ampere's law, but like after some kind of manipulation. So you use the Biot-Savart law. Why is that? Because it allows you to find the magnetic field from infinitesimally small current. And then if you have a current distribution, which is not like linear or like an infinite line or something like that, in that case, then you can integrate on anything. So the Biot-Savart law that gives you the magnetic field from an infinitesimal current applies to everything. However, in simple cases, like when you have infinite long structures, like it could be infinite line or it could be an infinite cylinder where the current flows everywhere on the cylinder and has cylindrical symmetry. In that case, yeah, I can go to the simple form, Ampere's law, and I can apply the Stokes theorem to get the magnetic field. But in the most complex case, then you use the Biot-Savart. Like the same thing applies in statics. If your charge distribution is not creating like some kind of a spherical symmetry or cylindrical symmetry, but is different, is like on lines that is like a triangle or it is a circle as we did, then practically you start with Coulomb's law and not with the um, Gauss's law. All right, so it's a similar thing. So you remember, you start with the simpler representations if your currents or if your charges create some kind of cylindrical symmetry or spherical symmetry, or like a plane is on an infinite plane. But if you get more complex, you start with, in our case here, magnetostatics, with the Biot-Savart law. And in this case, that's what we did, and we found this formula. Now, what I wanted to show here, let's assume we had, you remember I had put initially the two loops in some kind of a distance. And now I bring the two loops very, very close to each other, all right? And what happens when I bring them very close? In this case, still, the lines, the loops rather, have the same direction of the current. So if I bring them very close, and they're so close, so the distance between them is much smaller than the radius, all right, of the circles, of the loops, of those loops, then practically it's like the magnetic fields align everywhere. So especially around on the surface of the loop. So you see all of the lines going through parallel, all right? Both the purple and the green lines for both loops, they will go through aligned, which means that if I have two loops very, very close to each other in a distance which is much, much less, as I show here, you see here, I show that this distance that you see here, look at this one. I show that this distance between the two loops is much smaller than the radius. And when that happens, the two magnetic fields align, and practically is like, for two loops, is like the magnetic field that goes through the two loops is like twice the magnetic field that it would go through one loop. I could put three loops together, and three loops that have the same direction in the current. Then what would happen? Then the magnetic field through all of these loops will be 3 times the magnetic field from one loop. Why is that important? And I will come to the other things. Because if we can create a solenoid that we can wind around a bar, then practically is like, and then we throw a current, we let the current go through this solenoid. If I have 4 loops in the solenoid, then I can create a field, a magnetic field, that goes through each of these loops, which is 4 times bigger than the field that would go through one loop. Okay? And that is important because and it is going to increase the inductance. And do you see, that's what I wanted to say. Do you see why we use this one here in electric circuits, a symbolic representation of an inductance? Because that's the only way you have to create multiple loops to create an inductor. And if we are at low frequencies, how do we create inductors? We take like a small ferromagnetic material, It's like iron, all right, which is ferromagnetic. And why do we use ferromagnetic materials and not dielectrics? Because they increase even more. You remember that remember that B equals mu H, all right? And B is also the magnetic flux density. So if B is the product of a scalar and the magnetic field, what that means is that I can find a magnetic material that has a large mu. And large mu means it could be 10,000. There are ferromagnetic like iron. There are materials that have a very, very, very high mu. And if B, and then if mu is this high, then for a small magnetic field, I can create a very high magnetic flux density. All right, so B becomes very high. And why is this important? I will cover this and I will go back to other arrangements. Why is this important? Because if I have a very, very high magnetic flux density, B, then, and I integrate it over an area, that gives me a very high flux. And this flux, in terms of B, is extremely important. Why is that? Because if it happens that I have a loop, we're going to see it next time, but I'm introducing it. If we have a loop that has a current, and let's assume that this loop has a current and then creates its own magnetic field, then this magnetic field is going to create a magnetic flux density. So if the loop is around a ferromagnetic material like iron, then the magnetic flux density is going to be so high. And then if I integrate it over the surface of the loop, it's going to give me a very high magnetic flux. And if I take this magnetic flux, which is here, I show it with psi, and I divide psi with the current that produces it, that gives me an inductance. All right, so the inductance practically, that's why as we said before, the inductance is nothing else but a measure of the flux that can be generated and can be kept in one space, the magnetic flux. So it's a measure of the magnetic energy. So if I have a coil like this, and if I have now 4 times of the magnetic field that goes through, and I will show the magnetic field, if I have 4 times the original magnetic field, and if I have this coil around a very high mu material, then B over mu is going to be very high, excuse me, B, which is mu over H, is mu times H, is going to be very high, and then which means this is going to be very high compared to H, obviously, which means that psi is going to be very high as a number, and that means that I have a large inductance. And this is important. That means that I can store a lot of magnetic energy. And why it is important to have storage elements of magnetic energy, like we have storage elements of electric energy? Because we can time it. So I have electric energy that transfers from electric to magnetic. And then, so I have a capacitor next to an inductor. And then over part of the time, the charges go from the capacitor, they run to the inductor, they become a current. So the electric energy that was initially stored in the capacitor becomes magnetic energy in the inductor. And then after they go through a peak, the charges go back and charge and go and store at the 2 plates of the capacitor. So that half of the time, the electric energy changes into magnetic, and the other half of the time, the magnetic energy changes into electric. And that's extremely important because it creates circuits that have very important function. These circuits operate at high frequencies, and we call that the resonant frequency. So we have a resonance in the system. All right, so we use this. We use these inductors and capacitors together. And what do you do by using capacitors and inductors together? You can do filters. All right, you can filter frequencies. You use them to do matching for amplifiers. In receivers, you use them for all kinds of different things. Now, let me go back and say the following so you become um, a little more, talking a little more about getting the feel on how the magnetic fields develop around currents. I said here we have two loops and the currents are the same, all right? And then we see that when you have two loops and the currents are the same, on the axis of the two loops, the magnetic fields, their magnetic fields align. So you sum them up. What happens if I have not loops, current filaments, like currents that flow on straight lines? Now, there we go back and think on what kind of a magnetic field a current filament creates. And then we use the right-hand rule. And then if our current moves along my thumb, then practically the magnetic field is going to go how you see it here. There. Now, what happens if I take two of these wires that have the same now? I did exactly as I did with loops. I got the same direction of the currents. Now I put them one next to the other. So what happens here, which is different from the loops? Because of the way the magnetic fields, look at the magnetic field from the left current filament, the blue lines, all right? They circle the current like this, and look at the magnetic field from the current filament to the right, which is going the same direction. In between, then pay attention to what happens in this area. If I were to cut here, to create like a planar cut to these loops, to these currents, what I would see is that the blue lines in between the two currents here go inside the surface on one side of the current, they come outside of the surface on the other. That's how they circulate, all right? And now I go to the other current next to it. I look at the green lines and I see that in between the currents, the green lines come out of the plane, and on the other side of their current go in the plane. So for two current filaments that are parallel and have the same direction, the opposite happens from what we saw in the loops in between the two current filaments. In the loops, the magnetic fields align and we sum them. In the currents, they misalign. They totally have opposite directions, and which means that they will cancel out in between. So two currents flowing in this direction, they have the weakest is like in between, like at the center of these two currents, the magnetic field is going to be zero. But outside on the left of the current to the left, and on the right of the current to the right, you see here in this and in this, the two magnetic fields have the same direction. So they will superimpose. So in these two electric current filaments, in between between them, the field is the weakest, and outside of them, the field is the strongest. What happens if I have the same two filaments, but I select two different directions of the magnetic field? Now, the green magnetic field lines and the blue magnetic field lines in between the two currents will align in directions. So they will sum up in between the two currents. And they will subtract or cancel out outside. That is very important here. Why? Because we use this concept. You see, we use two current filaments that have an opposite direction to create transmission lines. Okay? Because this way you combine the field. You combine the field. So let me ask you this then. When you have, you know how we send energy, the power lines, all right? So we have the power lines and they run over ground. If we had only one line, so the ground, you know, is like an infinite, is like a very good conductor, especially at very low frequencies, because the power lines run at very low frequencies. Okay? What happens then if it is a very good conductor? According to the image theorem, which we are going to see later, if you have an electric current like this and ground and perfect conductor, the image of this is going to be an electric current that has the opposite direction. So practically a line, like an energy line, like a power line that runs over ground, is between the line and its image. There are two currents going in the opposite direction, which means what? That in between them, the magnetic field is the strongest. In between them, the magnetic field is the strongest. And away from them, it goes down very fast. So that's why when they have these power lines that run, have you seen the towers that carry them? They don't allow anybody to go and build a house underneath. Do you know how bad it would be to be underneath, inside this line? No, seriously. I mean, the magnetic fields are so strong that eventually will have an impact. They will on your brain. You know why? Because a magnetic field will start changing the orientation of the little, so the electrons do this electron spin, so they look like small currents that go like that, and eventually they will change the orientation. They will change the orientation of your neurons, and may not necessarily make you crazy, but you're going to have horrible headaches. And that's why people, so there are serious, if you go under the line, all right? And then usually you see how they have them, especially in high lines, they have a whole area that people cannot build there practically because of the high power that goes and the high magnetic fields. So in transmission lines, we try to contain it. By containing it also is not, people did not, in the beginning, I have to say, the last thing that they thought in the beginning when they were thinking about that was about safety. Usually, unfortunately, but safety comes next, all right? It is very unfortunate. It should not happen anymore because we need to think of safety at the same time we design things, which now we do. But the old days did not think about that. But the reason they still wanted to do this is because if you only have one wire, then you lose a lot of energy everywhere. So the energy does not combine and it does not go far distance because you're going to lose a lot of it. So you will need to have a tremendous amount of energy in the beginning of your wire to be able to send something respectable on the other side. But they found that if they have these two wires, one with one direction, the other the opposite, then practically you can combine your energy, you don't lose it, and you can send it long ways. All right, so that was the whole idea. So why am I using this as an example? Because you asked me what kind of a problem I can give you. If I go here, I may give you two loops in opposite direction. I have not designed the example, the meter, I have to tell you, but I could just give you two loops in the opposite directions with the currents and say, find me the magnetic field A. That could be a problem for the meter. I would not like you to go and solve it from the beginning. Now you could solve everything, assume that you know nothing and go and apply, Biot-Savart and then do it with two loops. You will never finish it. I'm telling you, you're not going to finish this problem in 45 minutes. But if you do exactly what I said I did here, you will be done with the problem within 20 minutes. That's how we want to think, all right? So that's how I'm going to ask you to give me a solution. Any questions so far?
So what was the advantage again of having the transmission lines have the currents going in opposite directions?
Because it confines the magnetic field, as you see here, in between the lines where the fields are up. Oops. And then outside it cancels out. So you keep the energy confined in a space. And then you can send more energy longer distances because you don't lose it.
Oh, okay, so it like conserves the energy that you
Right.
were sending.
Exactly. Mm-hmm.
Okay.
And that's how we started. But then obviously after that, when you start thinking about safety, you saw that at the same time you save people from being exposed to very high magnetic fields. Because being exposed to anything, either electric, very strong electric or very strong magnetic field, is not a good idea. All right. And usually in the electronics, you can say, well, I'm exposed in this, but this is kind of microwatts. Here we're talking about megawatts, all right, in the power lines. It's like 10 to the 12 order of magnitude between the two. That's the difference. That's why I can, even if it's not good to keep it on your, because of temperature of the heat, but that's the big difference. So it's not good to be exposed to very strong fields. Even in the MRI that is strong, we don't do an MRI every day. All right, it will not be acceptable to have an MRI very often. It's one thing to be, it's like X-rays. All right. And with X-rays, they put all of these things to protect you because X-rays, they do the same thing, but you don't have an X-ray every day. Otherwise, you will not survive it for too long. We have it, once in a while if we need it. Okay, same kind of thing. Any? Yes.
Um, if you had two transmission lines that were running in opposite directions, and so you wanted,
Two transmission lines, meaning there are four wires.
sorry, no, just one transmission line.
One, so two wires, yeah.
And so they're running in opposite directions, and you wanted the magnetic field to sum up in the middle and oppose on the outside. It's like that example.
Yes.
Um, in order to make that more efficient, would you?
The closer you go, the closer you bring the two wires, the better off
So it's not a matter of area or flux, it's just the distance.
The distance, like the same thing with the loops. The closer I brought the loops, the more I was able to confine around their surface. And that was good for inductance, all right, obviously. That was good because in that case, I want to make the magnetic field that is confined within these two loops very strong. Same thing here, I want to confine it. So the closer you bring them, the better the confinement. Okay, any questions?
So does it cancel out fully in like either the center or the outside there?
In the outside, it does not cancel fully, but the way it goes, if I were to plot it, it would go like this. Let me see. Something like that, you see? So it's not gonna be an abrupt cancellation, but it's gonna look like this. And then it keeps going down to very low levels.
Okay, makes sense. And then is it kind of the same for above where like the middle kind of like goes down quickly, but not like all the way to zero? Or just the one like right above that?
Yes, so here is gonna look like this, to tell you the truth. It's gonna look like, if I were to plot it along this line, let me make it a little smaller so I have space to plot. Okay, what I would find is that it will start strong here. It would go to 0, and then it will sustain itself here. See how it's gonna go?
Oh, I see. Yeah, because you have the different directions.
Yes.
Okay, cool. Thank you.
Yeah, you're welcome. Any other questions? Okay, so now let's try to do something. We'll start something different. Now is when we are going to start with this, and if we don't finish it, now is when we are using the Biot-Savart law to find the magnetic field. What do we have here? We have a section of a current line, see, from A to B. So it is not an infinite line as we did when we used the uh, Ampere's law. This one is finite, so we cannot use Ampere's law. What we do here is we start with the infinitesimally small area, which is here, you see. And then I said, according to Biot-Savart, this infinitesimally small area will give me this field, where dH, I call it dH because it comes from an infinitesimally small current, all right? So it's I dl, which is like the small length of the current, and then it has a direction. Why does it have a direction? Because the current has a direction, all right? So dl, practically, why do I have it here? There is a step that I ignored because we use it very often. So the step that I did not include was that this is IDL. So the infinitesimally short current that is incorporated in this DL length has a direction. The direction is the Z direction. And what I do, because the current is constant, I move it in front of the differential, and then I have the constant current times a differential vector. That is DL. And what is the direction of DL? Is the direction of the current, obviously, at that point in time. So at that point in space. And it's the Z direction. So that's what it is. Okay, and then I use, and I have it here again. And then I use the Biot-Savart rule. And one more thing, R. What is R? R, according to the Biot-Savart law, is the vector from the current, the infinitesimally short current, to the point of observation, P. All right, so R is a vector. And what are the two components of this vector? This vector, the way we have it, is on a plane, all right, the same plane with the z-axis, and has two components if we consider the cylindrical coordinate system. It's going to have a rho component, and usually rho component, it's always, when we say rho, it's like this direction. All right? In a cylindrical coordinate system, the rho component, or the a sub rho direction, is the direction along the radius, all right, in this cylindrical coordinate system. And you see what is the radius is this one, all right? Because P, as you can see it, is on a cylindrical coordinate system, where rho is the radius of the circle. Like that's in the cylindrical system, we have rho, phi, and z as coordinates. And here, the rho vector has one component along the a sub rho direction, and the value is rho. And the other component is along the z direction, but negative because the direction of the vector is downwards. And how much, if this is the coordinate system, and at this point, let's assume that this point, O, at that point is z equals 0, all right? Then from O to DL, where is the infinitesimally short current, I have a minus Z again because the direction of the vector here is going downwards. So it's not positive Z, it's negative Z. So the vector R, this vector R, has two coordinates. That is key in this one. The key in this Biot-Savart law is to identify these two vectors. If you do not identify these two vectors, it's going to be extremely difficult to solve the problem using Biot-Savart. All right? So when you try to solve problems, examples with Biot-Savart, try yourself. It's one thing to understand when you see something, is another thing to do it yourself. First read it, make sure you understand it, and then close the page, put it aside, and then try to solve the problem yourself. Then you're gonna see if you can repeat the solution, then you really understand the problem, obviously, all right? But these two things, identifying DL and identifying the vector R, is extremely important. As soon as you identify vector R, then you know its magnitude. The magnitude of the vector, to write it here, R, is equal to square root of rho squared plus Z squared. And if I replace this here, I find this integral is given both in the book. It's a known integral, obviously. And then you can find, what does this remind you? Does it remind you of something? Yes, electric field from a line charge, which is finite, very similar. Not one by one, they're not similar expressions, but they look similar. They have a constant in front, and they vary as 1 over the distance. That is very similar, all right, from the distance rho, vertical, from the current line, or the vertical distance from the line charge. And then they have, in the previous case, we had sine and cosine. Here we have only cosines. Okay, and that in this particular case, the magnetic field goes along the phi direction. Is very similar, therefore, the magnetic field is very similar in its direction with the magnetic field of a infinite long current, even if we get it from a section. Now, why is this important? I will do this on Friday, but I can tell you right now. I could use this exactly and tell you now, find for me the following. I give you a square, and there is a current that flows in this square like this. All right, and this is A, B, C, and D. And I go to the center of the square, and I can give you all of the dimensions. Let's assume this is A, the same current, and I can ask you to find the magnetic field. Okay, what are you gonna do? You're gonna take the magnetic field from AB, and how is this magnetic field going? It's gonna come up. So the magnetic field from AB, if I were to use blue for that, it will come up here like that. Okay, and then I use blue, and then I go to this light blue, which is on the other side. And how is it gonna come back? The same way. And then what do? I go to BC, and let me use red for this. And how is this gonna come? From the center, it's gonna come in the same way. And what else? Then I use the light red. In fact, I'm solving the problem right now. And it's gonna come also the same way. So at the center, the total magnetic field is gonna all be the same direction. So total H, total, is going to be the sum of H from AB plus H from BC plus H from CD plus H from DA, and they are all coming out of the board, whatever you want to call that direction. If you call, you can, if this is the X and Y, X and Y, out of the board is going to be your Z. All right, so you can call this to be the Z direction. So your H total will be H sub Z total, where H sub Z total is going to be 4 times the magnetic field from AB. And how much is that? This one here. All right, and it's going to be 4 times I over 4 pi. What is the distance between this? This is A over 2. All right, and then how much is this angle and this one? They are 45 degrees. All right, and in this particular case, you find that in here, because of the equal angle that you have, this is going to be times 0. And so here is going to be 0 at the center. Okay, but it's not true otherwise.
Oh, where'd you get 0 from?
It's cosine of B minus cosine, let me see, excuse me, might not be, sorry. I might, I'm sorry. I may have made a huge mistake here. So A, I want to see the angles that I did here. Okay, they're not equal. So here, I'm sorry, I'm totally sorry about that. So one is AB and the other is AA, is the external. So if one is 45, the other is going to be 180 minus 45. All right, so practically they will sum up, because cosine of 45 is going to give you what? Square root of 2 by 2. And then cosine of 145 is going to give you minus square root of 2 by 2. So they will sum up. So I said 0. So it's not. It's going to be 4 times that. Thank God. So square root of 2 over 2. And that's how you find it. So these two go with 4. And it's going to be I over 4 pi A times square root of 2. Yes.
Why are we subtracting from 180 if like it's right here in the square we're only looking about?
Okay, so here, these are the two angles they are different from the before. These angles have been defined differently from the ones we had from the statics, all right? You need to remember. Why they're gonna be, these two are 45 degrees. So this is 45. So this one is gonna be 135, but did I say 145? Yeah, 135, because it needs to, it's gonna be 90 plus 45, 135, but it's gonna be the same, like it's gonna have the, let me see, I have to make sure that I'm right, okay, in what I say.
I think we did use like 45 and 45.
Yeah, 45
Okay, went up.
cosine is 0.7, yeah. And 135 cosine is minus 0.7. I'm right. So minus and minus gives plus. So this one here is AB is going to be 45. And AA is going to be 135. All right, from the triangle. Here, 45 45, 135. And this is going to be square root of 2 over 2. This is going to be minus square root of 2 over 2. But minus and minus gives plus. So it's going to be 2 times. 2 times, did I put times 2? Okay, so it's going to be I pi a square root of 2, something like that. So that's how you would solve this problem, all right? You will not solve it from the beginning. And you will make, not like me, that I made a mistake with the angles. You will look at the angles very carefully. That's what I said. When you take the formulas, try to be careful in what you are copying. Like I was not careful here. See what I got? I got something totally wrong by not being careful to check. So I was asking you to do something that I did not apply and gave me the wrong result, even if the whole process was correct. So this is a problem that you can solve very fast without solving from the beginning. An example. If I don't give you a square, it could be like a corner or some sort. It could be something like that. Okay. So in any case, these are the examples how you can take something like this that we develop and then use it to do something more complex. Any questions on this?
How did you get the angle for AB and AA again?
AB, 40, because this is a square, all right, this is going to be, because it's a square, every side is identical in the length. This here is, if I see whether I understood your question, this here is half of the side, and this is going to be half, and also this is a rectangular. So every one of these angles is going to be 45 degrees. So this is 45. And according to this here, one angle is the 45, the other is going to be the external, 135. Is that what you asked?
Yes.
Yeah.
And I know which one's the external, which one's the internal.
The external is the second. So the external is the one here, is this one. Okay. So that's the one that is 135 for our application. Here, the one that has the negative sign in front. Any other questions? Okay, so I will see you either later today for the problem solving session or on Friday. On Friday, we're gonna solve problems like this. Okay.